Okay, so a lot of these slides have been prepared by a lot of teachers before me. I don't claim credit to all the animations, they're really well done. So as the 20th century progressed, there were many problems, right, that classical physics could not provide a solution to. As physicists sought new ways to solve these puzzles, another revolution took place in physics between 1900 and 1930. A new theory called quantum theory was established! Exclamation mark. Right? So today we're gonna do this, right? Quantum physics. So what's one picture, right? If you ask yourself, what's one picture that can represent this chapter? Quantum physics 1. Right? It's actually this, you look. Right? It is a light that's coming out. But when you see light, do you see particles coming out? No. Right? You see light, you just see light itself. And then you ask yourself, what is that light? We have learned in previous chapters that this light is a wave. Right? We have learned in previous chapters that this light is a wave. So that's my introduction. We're going to introduce to you in more detail, right? So as I'm talking to you about the intro, right? Talking to you about intro, you need to ask yourself this one guiding question. Very important. Why do we need a new theory? Why do we need a new theory? Right? In science, we always say that the previous theory is true until proven otherwise. Right? So this chapter shows you, I'm going to bring you back in time in history, right? To show you what the scientists were thinking. Okay? So before 1900s, right? In fact, I've written it in the notes. It's around in 1800, 100 years ago. Right? Young's double slit experiment proved that light behaves as a wave. Right? If you have learned superposition, which you all should have, and remember, you know that superposition requires that light behave like a wave. Right? You can only superimpose waves. Right? Then next, diffraction of light as well. Right? Only waves can diffract. Only waves can curve around. Right? So this was the idea that led scientists to believe before 1900s that, oh, okay, light is a wave. Right? However, this is a classical wave theory. It could not explain a few things. Right? It could not explain, number one, the black body radiation. Number two, photoelectric effect, which is the main idea of this whole set of notes. Line spectra and production of X-ray. These next 3 and 4 are in quantum physics number 2. So let me talk briefly about black body radiation. It's not exactly in your syllabus, but it's really worth talking about because it's really what set the stage for photoelectric effect. So black body radiation, what is it? In the classical theory, right? So you just look at the dot line first. The classical theory states that for an object and for a black body, the wavelength emitted, right, will have higher and higher intensity as the wavelength gets shorter and shorter. Right? That's what it meant. They did some derivation, right? They derived, like, oh, if light is a wave, this is what it have, blah, blah, blah. When I hit out an object, what kind of waves will it come out? That's what they did. And they found this. The classical theory found that as your wavelength got shorter, the intensity gets higher. This naturally cannot be. Right? In fact, this was called the ultraviolet catastrophe. Why? Because as you get shorter, you get closer and closer to ultraviolet light. Why is that catastrophe? Because why? It means that there's free energy, right? Anything will keep emitting more and more energy in the ultraviolet and below region. Cannot be, right? Also, when you did an experiment, we realized this. Something that's cool, right? The peak color, peak wavelength is something quite long, maybe infrared. Something you heat up more, the wavelength becomes shorter, maybe now it starts to glow red color, or glow in some other yellow, bright orange yellow color. And you heat it some more, the object becomes even hotter. right? The peak value could be somewhere in the ultraviolet range. But as you if you look at the wavelengths after that, it all goes and tends towards zero. So this is the reality. The red, blue, and green lines are the reality. And it does not coincide with the theory. And for science, this is actually a very, very important thing, right? Your theory and your experimental results must meet, right? If not, it means that theory must be wrong, or that another theory must replace it. So this got scientists very perturbed, right? Oh, then how do we solve this? How do we solve this? Right? How do we solve this? So what happened? Planck, Max Planck. You all don't have much chance to hear Max Planck. I think I'm the only teacher that will talk about it. Right, Max Planck, he's one of the early scientists. He said, okay, let me try to solve this problem. Right, so he just tried to solve it mathematically. Right, okay, what can I model? Right, what can I assume to get this kind of curves? And he did it. He managed to solve it. Right, he resolved this problem, right, by adding a factor behind e to the power of something, right? But as he did that mathematically, he solved. He used math to whack the problem. Boom, problem solved. When he looked at the result, he said, if this is true, deriving from the result, it means that the energy of light must have discrete values, which was a shocker at the point of time. Which is a shocker. Why? Because if light is a wave, the energy that light can take can vary from 1 to 1.00001, 1.00002, so on and so forth, all the way is continuous. But what Max Planck found out was the energy was discrete. It starts with 1, the next energy is 4, then maybe 9, then maybe 16. Why cannot be Then it's literally the world of physics was torn apart. Like, what you always believe in now is no longer true. It's like when you realize that your parents also can make mistakes. Very sad. Right, because I share my own experience. When I was very young, my parents are the superheroes, right? And I realized when I get older, my parents also make mistakes. Why like that? Very sad. But it's true. So it is the same kind of feeling. It's like, everything that I believe in is no longer true. Oh no, how? But this is very important. This thing that Max Planck that he got, will later be used by Einstein, another giant, right? Another giant in our physics, to prove the photoelectric effect. Okay, very, very important. So this step, Max Planck set the stage. Another important thing or interesting thing about Max Planck, also not in your syllabus, is that h is the smallest constant you will see. It's 10 to the power minus 34. It's very, very small. Okay. Right. So today we will start fully on the photoelectric effect. So I finished. I'm still on the introduction, right? No, I finished the introduction. Right. The introduction. The question was, why do we need a new theory? And the answer is, well, the results experimentally and the theories don't match. Okay. So let's see if we can find some way to resolve this conundrum. Right, so as we talk about the photoelectric effect, and I introduce to you in more detail what the photoelectric effect is, I want you to have this in your mind, right? These are the two questions that we're trying to answer. When you do a photoelectric experiment, what observations contradicts with wave theory? Right, that means what the experiments show, how does it show that it cannot be explained by wave theory? If it's wave theory, then the result shouldn't be like that. Then second, how does it actually suggest the existence of photons, photons are particles of light? Okay, these are the two questions that you need to solve. Okay? So let's first briefly explain what the photoelectric effect is. Photoelectric effect is this. You shine light on a metal, an electron comes out. Come out. Electron comes out. That is essentially the photoelectric effect. You shine light on a metal and electrons come out. I say again, you shine light on a metal and what comes out? Very good. Wow. Hi, thank you. Right, so But then you realize this, right? Photoelectrons are emitted when the light frequency is high enough. What do I mean? Right? There's a certain frequency before light is emitted. What do I mean? So I show you. Shine purple light. Purple light. Purple, violet, the wavelength is short. It's around 400 nanometers. Right? The frequency is high. Okay? So when I shine light, I collect. How do I know electrons come out? I put a collector here. There'll be flow of electrons. Okay, so one more time. I shine light. Electrons come out. It's collected. How do I know electrons have came out? I can't really see electrons in the air. I collect it with a collector. Pass it through an ammeter. I measure it. Okay? So the problem is this. When you shine a low frequency light, nothing happens. Okay? Nothing happens. So this was the first thing that scientists noticed. How come no electron? Huh? How come no electron? Why? Then they went to check all the wires, right? Because in lab, we also experienced this before. No electrons, could be my wire spoil, maybe my ammeter spoil, maybe my switch not working. Now you go and check all this. Maybe my metal spoil. But check everything already, check everything. Yeah? So when they use purple light, it worked. When you use red light, didn't work. You're like, why? Why like that? Never mind. Maybe the torchlight not strong enough. Instead of one torchlight, let's use two torchlight. Two torchlight of red color. See, more arrows coming in now. No electrons. Still no electrons. I increase the intensity. Nothing happened. So that was the conundrum that the scientists had when they're doing this experiment. Why? Because according to classical wave theory, that means before Einstein's photoelectric effect, this was what they believed in. They believed this. If I shine light on metal, watch the metal. I shine light, the metal will slowly become hotter and hotter, and once the electron gains enough energy, it will come out. What's the analogy? The analogy is this. If you need to go to USS, Universal Studios Singapore, okay? Just in case you don't know, right? And you need $70, right? Entry price $70 still? Yes, around there. I give you $1 a day. $1. 70 days later, will you be able to go to USS? Yes, this is the analogy, right? I give you $1 of energy. If you need $70, you just wait until long enough, you will get enough energy and you will go up. That is what classical theory believes. This is what classical theory believes. But did it work? Did it work in the quantum theory? It did not. It did not. When the light you gave did not have enough enough money, enough energy, no matter how long you shine in there, no electron come out. They refuse to come out. It's like they need more money. It's as if like that. It's like, I need more energy if I can come out. Very interesting. Right? In science, the most interesting things is when it contradicts with your previous assumptions. Alright, so first is this. Right? It only comes out when light is above a certain threshold frequency, and no matter how much more torchlight you use, as long as your frequency is below, let's say you use a red color, you use 10 torchlight, also no use. No electrons will come out. Very, very strange. Very, very strange. If I go back to the USS analogy, then like, okay, if one Mr. Ho give me $1, I don't come out. How about 70 Mr. Ho give me $1? Shouldn't I also come out? Because I got 70 in one day, I should come out. But no, in this case, still no. Very interesting. That means you can only take the energy from one person, something like that. That's the analogy. Very, very interesting. Alright? So this contradicts classical wave theory. Number two, wave theory again says I can accumulate the money over time. I can accumulate, slowly become hotter, and the electron comes out. Right? That's what I said. And accumulate means I can wait a long time before it comes out. But again, this is also not wrong. This is also wrong. Sorry, this is also wrong. Why? Because they realize that the moment you shine light on the metal, the electrons come out immediately, instantly, boom, it's just there. Right, so the scientists were literally looking at a puzzle that they cannot solve. They're like, oh no, how? Who can save us all? Is physics not true? Oh no, right? And regardless of how weak the intensity of incident light is, this is the other point. If I use a purple torchlight and electrons is coming out, I can turn the torchlight dimmer. Still got electron. I turn it dimmer somehow. Still got electron. I turn it until very, very, very dim. Still got electron. Eh, why like that? They also do not understand. Okay? So this also contradicts with classical wave theory. Okay? Next. Watch, can all look at the screen again? Ready? 1, 2, 3, go. If you shine more intensity, the electrons, look at the right side, should have more speed. Okay, come on. Okay. One more time. Faster on the right side, slower on the left. One more is coming out. Wait for it. It needs to gather. Okay, there you go. And slower on that. Okay. So this is what wave theory is, you know. It says that if I shine more energy to it, you accumulate more energy, you come out with more energy, right? That's what it says, and it makes sense, right? If I give you more, if more Mr. Host is giving you $1 a day, you will eventually get more money a day. You will have come out, you have access, you bring $140 to USS and have 70 left over. Correct? That is classically what it is. But is it true? No, it's not. Again, mind blown. Right? Literally mind blown moment. Huh? They don't have that word at that time, but yes, that was what they felt. What did they see? What they in fact see? They saw that when the moment you use a certain colored light and you shine on the metal, there was a fixed maximum. There's still a range of K kinetic energy of the electrons. The electrons that came out, they were slow, they were fast, but there was a fixed maximum. There was an absolute maximum energy. Very, very interesting. Okay? And this was regardless, once again, regardless of the intensity, regardless of the number of torchlight you're using. Okay? Again, this contradicts wave theory. The last observation number 4, is that the higher the intensity, the larger the photoelectron emission. What is this? Listen, just now I said, what contradicted? I shine more torchlight, it does not mean that the electron coming out has more energy. But what they saw was that if I shine more torchlight, more electrons comes out. Okay, this is what they observed. And this one, both of them agree. Quantum said, okay, yes. The classical wave also yes. And they both of them agree. Okay. Right, so test yourself. Right? What are the 4 observations of the photoelectric effect? Without referring, what were they? What were they? First, was that there must have been a threshold frequency. That means there must be a minimum frequency for electrons to come out. Number 2, the electrons comes out immediately. Number 3, what did he say? I also forgot. Correct, the energy. Right, what does it say? For light of any frequency, there is a maximum value, regardless of the intensity. It doesn't mean that if you shine more light, the electron comes out with more energy. No, it just means more electron comes out, which is observation number 4. Okay, so the first 3 contradicts with classical wave theory. Okay, are you able to follow me? Can? Any questions at this point? This page, can you put a very, very big star? This page, very, very important. Okay? They often like to ask how did photoelectric effect show that light behaves as a particle? So you state the first three observations and the reasons. Okay, Ken? Right. If you have no questions, then I'm moving on. Okay, animation again. Look at the screen. In 1905, Einstein proposed a theory to explain these four observations. According to him, the incident light was not wave light, but particle light. Later, these particles are called photons. Right? So in that running script, there's one phrase that I need to stress. Right? Yesterday I had a lecture. I immediately went to check with some of my students. Do you know what a photon is? They said, electron? And no, okay. Photon is what? Photons are particles of light. Electrons are the thing that carries a charge and runs your electricity. Okay? But here, I want to introduce to you what is it called. Why is it called the photoelectric effect? Remember at the very start, I said what is the photoelectric effect? You have light coming in and you have electrons going out. So light, when you take a photograph, there's a flash, there's like photo, light. Electric is the electrons that come out. Okay, so essentially it's light producing electrons. Light producing electrons. Okay, that's the photoelectric effect. Right. Wow, they say, hey, Mr. Ho, you can finish this in one lecture. Huh? No, not. The 3.1, 3.2 will take many lectures, okay? To really know it carefully. So, starting from 3 is where the bulk of the knowledge is, okay? So, really pay attention. And as you can see, the guiding questions for here, there's only one, all right? What is the energy of a photon? Okay, what is the energy of a photon? How did Einstein, how did Max Planck call it, right? How did he do it? So, Einstein explains photoelectric effect. Previously, they thought you just shine light and you get electrons. But Einstein said, look, the light that you shine is not a wave. It's better explained if the light that you shine is a particle. Particle comes in, comes out. You see the difference between these two animations and before? What did I do before? Before I showed arrows. Just arrows. I didn't draw any particle. The arrows could be waves coming in. Now I draw particles. Okay, this is important. That means that you are having particles coming in, like ping pong balls coming in, and hitting out, I don't know, a baseball, something like that. Okay? It's not actually the actual size, but that's what you get. Okay? So previously, Planck decided, right, I found out that the energy of the photons is HF. Okay? Later on, you also measure the energy of the electron. There is a way to measure it out tissue. You found that it's actually the energy of the electron is the energy of the light minus the energy they require to pay to the metal. Okay? So this is the brief overview of how Einstein explains photoelectric effect. Okay? So now, let's introduce to you what Einstein decided. What is a photon? Okay? Photon is an indivisible quantum or packet of electromagnetic energy which is emitted, transmitted, and absorbed as a whole. Each photon is given by E equals hf, and these are the equation. And h is the Planck's constant, f is the frequency of electromagnetic radiation. Right. At this point, can you take 30 seconds to memorize what is a photon. Right? What is a photon? Cover. Check. Okay, 1 minute, 30 seconds. Okay, 1 minute to do it. All right. Quite cool. The photon is, I need to stress on the importance of this because it is indivisible. If you have a wave theory and I have 10 units of energy, I can give 5 to somebody and give 5 to somebody else. But when you're a photon and you have 10 units of energy, you either give all or nothing. You either give all or nothing. That is very interesting. This one is like, is there a song like that? Maybe there was. There's probably a song that says you have all or nothing. Okay? Probably. You all find it, please let me know. Anyway, example 1. Okay, so how do you find the energy of orange light? Orange light of this wavelength. Okay? Well, E equals HF. Right? But here, frequency, you are not given. Then how? Here, you need to know what is the speed of light. Okay, it's assumed that you should know. The speed of light is 3.0 times 10 to the power 8. Okay? 3.0 and 10 to the power 8. So using V equals to F lambda, the velocity equals to frequency times lambda. In this case, we use velocity, we always write as C. Right? We always write the velocity as C, speed of light. You rearrange, sub it in, you get an answer. Great, quite easy. This is to warm you up. Okay, warm you up to what is the energy of a photon. So, in the previous part, in 3, when I explained Einstein's photoelectric effect, he showed, right? He showed that it was actually photons coming in. But now I'm going to say it again in more detail, right? Why there's a threshold frequency, why there's a maximum Ke, why is a range of Ke, so on and so forth. Okay, so these are 3 guiding questions. Why is there a minimum threshold frequency? Why is there a maximum Ke for electrons? And why is there a range of Ke for electrons? Okay, so the first one belongs to what is coming in, the light. The next 2 belongs to what is going out for the electrons. Okay. Scary, huh? But let's take a look at this setup first. Let's take it step by step. Let's look at the most important one. The photoelectric effect. You have a metal which emits electron. Okay? So this is the metal that emits electron. Okay? This is the metal. This E is the emitter. And this C is the collector. Notice that both of them, all of them are enclosed within a chamber which has the word vacuum in it. A word vacuum. Why must it be in a vacuum? Why must it be in a vacuum? Anyone? Anyone knows? Discuss to your left and right. Then raise your hand. Who knows? Okay, last row, my class, come. Why must it be a vacuum? What? Oh. Don't know. Okay. Last row behind. Daniel's row. Why must it be a vacuum? I'll give you a hint. What are you shining in? Light. What is coming out? Electrons. If there's air inside, what happens? Last row, come. Loudly. No. Last row, that side, on my left. Why is it that there's a vacuum? Come. Shout out your guess. Ivan knows the answer. Very good. Ivan, courage. Come on. Try. Just try. Got your head. Nice. Angry lah. Hey, recording this, sorry. Come. 6-2, come, save me. Bruce. Depend on you already. Why vacuum? Why not just air? Yes. If it's not vacuum, what do you emit out? It is electrons, right? It's important, right? If it's electrons in air, do you feel electric shock when you walk through the air? No, right? Why? Because the air particles, water, carry away the charges. So if I ask you, if you have air here and your electrons are coming out, will you collect everything? No, right? And we are in scientists. We are very, very precise. We want to measure every single one of them. Can you have half of them disappearing and don't know how to account for them? Why you want to make your life difficult? So make a vacuum. Boom, there you go. Okay, so this vacuum I explained. Next, why is it a quartz window? The whole thing is enclosed. Quartz window allows light to come in like that. So quartz window is essentially just for light to come in. So when you why do you not have the whole thing in quartz? Is it? Cannot be because too expensive. Okay. To design something stable like that. So when you have the light come in, electron comes out, goes to emitter, goes around. Okay. So what are you measuring? You are measuring the current. You are measuring the current. And look, can you now look at this side of the setup? Right hand side. What do you have here? You have a battery, positive, negative. So if it is negative here, can you see that the emitter must be negative? And you have positive here, the collector must be positive. Which means that every electron that comes out sees that this side is very positive and this side is very negative. Where will they go? They'll always go to the collector side. That means all electrons that come out should and would be captured by the collector if it's positive enough. And how do you change that positivity? You vary around here. This is a potential divider bar. You move this arrow up, it becomes a lot more positive. You move this jockey down, it becomes very, very close. If you move it all the way down, exactly here at 0, you get neutral. You get neutral ends of the collector and emitter. Okay? Right, I explained the setup to you. Now we can talk more science. Okay? This is what we have. Moving on. Using this setup, they realized this thing. They realized that the energy of the incident photon, they could measure it because they know the frequency of light. After the energy of light that comes in, it pays a certain amount to the entrance fee, right? Which is the work function of the metal. The rest comes out as the kinetic energy of the electron. One more time. So this is actually a conservation of energy. If you have 100 joules of energy, 100 units of energy coming in. You pay $70 to enter USS. You have $30 left to play around. That's essentially what it means. I bring $100 in. I pay $70 to get into the entrance fee. I get $30 left. But here, I need to use more professional language with you. What's the entrance fee? It is a work function of the metal. It is how much energy you must give to the metal. Okay, so essentially the work function of the metal is how much energy you must pay to the metal to emit an electron. Okay? Any questions?
For your HF, right, what's the energy in the form of? Or is it even
It's in the form of joules.
not? I mean, like, is it even reasonable to ask what energy is in the form of? Because you can describe it as kinetic energy for, like, for example, half equal MV or half MV. Is that even a question that can be asked?
It's not exactly. Wait, let's talk about this in more detail. I need to ask more questions and it might take a bit long. Okay, good question, but let's ask it in more detail later on. Right. Okay, so if you have no other questions, can I ask you a question? Okay? Wow, very good. Why is there a maximum number here? Why did I say here the energy of electron is the maximum in this equation? The maximum. Not just any energy, but the maximum. That means Einstein photoelectric effect equation. The Ke is maximum. Why? That means in this equation, they are measuring the energy of the fastest electron, the most energetic electron. They are measuring 1 point in the graphs later on. Just 1 point, one single point, the most extreme one. Okay? For this to have the maximum energy, it means that you have paid the minimum sum to go in. Right? That means the work function of metal is the minimum energy that you must give to the metal. So can you write it down? The work function of metal is actually the minimum energy. Highlight it in the next line. It's the minimum energy you need to pay to the metal. That means sometimes you go USS, there's $70, there's $65, there's $60, there's some discount. You use the minimum amount. Okay? So work function is the minimum energy needed to take an electron out of the metal. The symbol is once again phi. Looks like your flux symbol, but well, we ran out of Greek symbols, no choice. Here I also want to introduce to you one thing, or remind you of what the electron volt is. Okay, what the electron volt is. Electron volt is the amount of Ke gained by electron when it's accelerated through 1 volt. You should have learned this in electric fields, but I need to remind you because sometimes they express the energy of the electron in EV rather than in joules. Okay, so here, watch, we accelerate it across. The Ke there is 1 EV. When I accelerate 1 electron across 1 volt, the Ke gain is 1 EV. Okay? And that is given by this number. Can you highlight this? Oh, I got students say 1 EV is a unit. They say EV is a unit of some strange E and volts. It's not. 1 EV, yes, it's a unit, but it's a unit for energy. They think that it's a unit for volts. Or they thought that 1 EV is 1 times 10 to the power 6. Wait, 1.6 times 10 to the power minus 19 volts. Wrong. It's not. It's actually for energy. Right? So please note this. Because sometimes we will convert the Ke electron in EV. Right. Oh, finally I can talk about this. Oof. So how does Einstein, I promise you this, so I'll finally say it. How does Einstein's photoelectric effect explains this observation? Number 1, from his equation, HF equals to, it means that the energy you shine in must be larger than the work function of the metal. work function of matter is how much energy, the minimum amount of energy you must give to the metal. It must be larger than or equals to. Right? Larger than or equals to, which means that there is a minimum, which means that there is a threshold frequency. Okay? There is a threshold frequency where the threshold frequency F0. F0 is the threshold frequency. Can you highlight it? It's in the box, but can you label that? I put an arrow to it. F0 is the threshold frequency is given as equal to the work function of the metal. Hf0 is equal to the work function of the metal. So this explains why if your energy coming in is less than the work function of metal, nothing comes out. But it's quite evil, this work function. If you think about it, if I use a USS analogy again, it means that if you bring 60, let's say the entrance fee is $70, you bring $50 of entrance fee, they'll just eat your $50 and say, bye, you cannot go in. Right? They take away the energy and say, okay, that's it. Right? Which is kind of weird. Oh, it's kind of weird. They take your energy and give you nothing in return. Very, very, very strange. Next, observation number 2. This is very interesting. This explains it very, very clearly. Observation number 2 that we saw just now is that there was no time delay. No time delay. When it's coming in, the photon comes in, it hits out the electron. No time delay. Why does it explain it so well? I give you another analogy. Soccer. I take a soccer ball in the air, and I kick it. Then the soccer ball vibrate in air. Then boom, fly off. Got see before or not? Shaolin soccer. Okay. Okay, I was hoping for no, but okay. In reality, not in movies, you will never see this, right? It will be very strange you can actually do that. Right? Why? Because it's a particle interaction. The leg interacts with the ball has to move away. It's not a wave particle interaction where the ball can slowly accumulate energy. So the photon, Einstein's epiphany was that, oh, it is just like that. It is a particle coming in, interacting with the electron. So it has to be, every electron that comes out must have, listen very carefully, every electron that came out must have interacted with a photon. Where photon is a particle of light. It must have. It must have. But it doesn't mean that all photons will interact with electrons. I say again. Every electron that comes out must have interacted with a photon. But not all photons will interact with electrons. Okay, here I just show you the lucky photon, the one that hits the electron. Later on you will see that actually it's not true. Not all of them will interact. But anyway, the point here is that there will be no time delay. Observation number 3. Why is there a range of speeds? Right? Why is there a range of speeds? And why is there a certain maximum? So this one I need you to look at the screen and look carefully. Look, this one coming in, electron goes up quite quickly. Second one, electron comes in, photon comes in, electron goes up very slowly. Okay, so here's the game. Find the difference. Other than the speed, in a still picture, in these two pictures, find the difference. 10 seconds. 10, 9, 8, 7, 6. Shout out your answer. 5. Sorry? Correct. The electron is in the middle. Very good. The last lecture, nobody could do it. Very good. Okay? Maybe they just shy, they don't say. Okay, but what's the difference? Look, I ask you, treasure hunt. I put the treasure on the sand, and I took the treasure, I bury 1 meter in. Which one is easier to take out? The one on the surface, right? So this is exactly what is happening. I put the sand. What is easier to take out? This? Is actually, this is exactly what the electron that is right at the surface comes out more easily than the one that's buried deep inside. So imagine your photon coming in has $100, $100, $100 joules of energy. The one at the surface, you just pay $70, boom, it comes out. It comes out with $30 worth of energy, or 30 joules of energy. This one goes further in, you pay more than $70. Oh, I don't know the entrance fee where you get from, but you go to this USS, the entrance fee is $80. Oh, I cannot con already, but whatever, you die want to go. You pay $80, but you left with only $20. Right? So that's the difference. The electron is further embedded inside the metal. It is harder to come out because of all the potentials, and it needs to overcome to come out. Okay? Hence, there's a range of speeds, but a definite maximum. There's a definite maximum, but there's a range of speeds. Okay? Right. Number 4. How does Einstein's photoelectric effect explain the photoelectric current? So current is defined by rate of flow of charges per unit time. The total charge is given by the number of electrons multiplied by the charge of an electron divided by time. I take out the charge of electron. I have the rate of flow of electron, Ne per unit time. Ne is the total number of electrons, so this is the rate of flow of electrons times the charge of electron, and this is the current. Okay. Next, the light intensity is a measure of the rate of arrival of photons. So this one, so this is not the same. This I is for current. Can you highlight? This I is for current. The next one, intensity. A lot of my students also have to put I. Don't put that. Put INT. Right? Put intensity. Not the same thing. Intensity. Intensity is a measure of power per unit area. Power per unit area. So power is energy over time. So intensity is energy over time over area. There's a very easy way to remember this. It's called I eat. I eat. E-A-T. I eat. Okay. So energy of the photons. This is for light. For light. Is the number of photons times the energy of a photon. Follow me? Energy, total energy is number of photons times the energy of a photon. You redistribute everything out, take NP over T, you got the rate of arrival of photons, multiplied by the energy of a photon per unit area. Wow. This one, quite important. Okay, quite important. We're used very, very, very often. So how does it relate? How does this Einstein's theory explain the increased number of electrons? Right, observation number 4. Why are they more electrons when you increase the intensity? So watch this. On the left hand side, you have 2 photons represented by 2 photons coming in. Come in, 1 electron go out. Okay? Let's say it's 2 to 1. On the right hand side, if you have 4 photons coming in, how many electrons must go out? 2, right? The ratio is fixed. Okay? But please do not go away. This is a representation. In fact, right, every electron that you come out is 1 in a million. In fact, you need about 1 million photons to get 1 electron coming out, around that. So every electron you see is actually quite the lucky one. Okay? Right. Pause and think. Pause and think. Photoelectrons are emitted when light is shone on a metal surface. What happens to the maximum K electrons when the frequency is increased? B, the wave function increases separately. Okay, discuss with your friends. 2 minutes, go. Is the pace too slow? Right. Okay, discussed. Right, what happens? Look at the equation. What happens if the frequency is increased? So first you write out the equation. HF equals to K max plus phi. Remember, phi is the minimum. If the frequency is increased, your K max must actually increase because this is constant. Right? So if frequency is increased, K max must be increased. Why the work function is increased? If this is increased and frequency stays the same, K max must decrease. Okay? A simple exercise to jog your brain. Right. Let's go a little bit more. Example number 2. Light bulb emits a wavelength of this. Why don't we just end here for today? It's already 9:14. Right, we have enough time, I think. Next lectures, we'll start with example 2. Go and read it in advance. So the next lecture, we come back, we will be able to do this. So what did I do with you today? Shh, hold on. Shh, ladies and gentlemen, wait. What did I do with you today? I covered the intro. Shh. I gave you an understanding of what the photoelectric effect. I gave you the Einstein's interpretation of the photoelectric effect. I gave you the formula of the photoelectric effect. I also explained to you the experimental set. I did 5 things with you all today. Very good. Thank you for being such a good audience, right? Next lecture, we're going to do a lot more. So go and revise this. Make sure you know everything I've covered today. If you have any questions, if you have any feedback, please come forward so that I can answer it immediately before the next lecture, which happens to be tomorrow. All right. Thank you very much. See you tomorrow. Bye-bye.